All right, here's our scenario, 2633 coming in today. This, I mean, you got the vibe of the class by now. It is just like continuous, right? So you miss a day, you really need to watch the lecture, get that work done and struggle with it if you have to, because that's the way this class rolls. We're gonna get 8 chapters for sure, 9 if we're next level. Yeah, I know, that would be next. That's a chapter a week, pretty much. Since we had a week off, it's only a 9-week term. Yeah. All right, so 26 and 33 coming in today. If you don't have them done, get them done. This is the last week I'll take late stuff unless you communicate. So that was, I hope, clear. Like if life's rough and you send me an email, I'm not gonna get my homework in today, that's fine. If you just don't turn it in, that's not cool. Weeks 5, 6, 7, 8, 9. All right, let's do these. 26 and 33. You have 42 and 44 to do as homework, so we need to make sure we get to some angled forces, because right now we're just doing these parallel forces. Right, all vertical, the easiest. They might feel easy, but they're not too bad. Once you get the system down, they're not too bad. We got some wiring issues. Right, and it said find the resultant. Did it say with respect to a point? Or did it just say find the
I think
result?
it's A on the left. The triangle.
Oh yeah, with respect to A. So the problems are gonna do that for a while, and then it's just gonna go away on the exam. I'm not gonna say with respect to A, I'm just gonna say find the resultant. You will then choose wherever you want to collect the forces, okay? So they're asking you to, when they say with respect to A, they're saying like, hey, collect all the forces at A and then distribute that resultant back out. Remember, our goal is to turn 1, 2, 3 forces into one force, right? We're gonna get rid of all 3 and we're gonna just have one remaining force. So I didn't go over the reason why we can do what we're doing. The book does, so if you read, it's gonna talk about couples and creating these moments, right? The system is, if I wanna collect everything today, I move everything over there. The 300 comes over. Right? I keep its translational effect, it's down 300, so I keep that. But then I have to bring the moment with it. Right, so there's gonna be 2 things that you have to collect. The transitional X and Y, these are all Y, so we don't have any X's yet. And the moments. So what's the moment for the 300? Yeah, 3 times 300 is 900. What's the unit? It's foot-pounds. Yep, feet-pounds, not feet per pound. It's not that, right? It is feet times pounds or foot-pounds. And what's its rotation? Yeah, so I put it in like this, just to think about it. That's clockwise, that's negative. So it's gonna go here at 900 foot-pounds. So you can collect it graphically, that's kind of what I've been doing, or you can actually write it out, you know, the moment at A of the 300 is 900 foot-pounds. Negative direction. I write it like this because it's just easy to see all the arrows if it's not too complicated of a problem. So now the 450 comes over. And we bring its moment is what? 450 times 8, right? 3,600, yeah. So that's also here. And then the 200 comes over. So I think I might have enough room for the 200. And its moment. I'm just gonna put it down here. 200 times 16. 3,200. So that gives us our resultant force, right? It's just add them up, 3, 500, 950. So R equals 950 pounds. So the vectors are just in pounds, right? And then the resultant moment is, what'd you get? 7700 foot-pounds. And rotating clockwise. Yeah, and this is all at point A. Agreed? Yeah, so that's collecting it all. Now our beam's still here. And what we want to know, the last step is like, okay, there is a force here and a rotational effect. So that means the force must be out here on the beam somewhere, creating that rotation. 7700. Right? Now I know R moves this way because I need to create the same kind of rotation. R could not move this way.
So you say the 950.
950 from just adding the vectors. 3, 2 is 500, 450 is 950 down. Add them up.
What do we multiply by the distance?
We did moments to get the 360, the 900, and the 3200, right? So we went 300 times 3 to get 900.
Right.
We did 450 times 8 to get the 3600, I think.
Right.
And we did 200 times 16 to get the 3200.
And then, but we didn't add those up.
We did 7700. If that's right. The engineering firm is confirming that number. Devin stumped.
3200, 3600, and 300?
Yeah, no.
None.
What are the moments? The moments are 900 foot-pounds, 3600 foot-pounds, 3200 foot-pounds. These are just pounds up here, vectors. So we add up all the vectors, we get 950. We add up the 3 moments, we get 7700. Okay? Resultant moment, resultant force. Now, to determine which way this goes, because you're going to end up with problems where you might collect all the forces in the middle of the beam, right? There's strategic reasons why we might collect forces at the location of a force. Like we could have collected the forces here. I wouldn't have had to move the 300. It's already there.
Then you have to keep track of like the.
Oh yeah, you have to keep track of everything because the resultant could move either direction, right? If you choose an intermediate point. So that's why I'm trying to say like, hey, this has to go this way because we have to create this effect. So this force out here somewhere creates this effect. This force over here somewhere would create that effect, which is not the same. So that's incorrect. That makes sense? The moment tells you which way you're going to move it. So the moment's telling me, oh, I'm moving it out here some X distance, right? And I know that the moment is equal to force times, I'm gonna put in X because I used X. Here, I'll make it perpendicular distance, right? And I know the moment is 7700 and I know the force is 950. So this perpendicular distance is going to be 7,700 foot-pounds divided by 950 pounds. The pounds cross, we're left with feet. So 7,700 divided by 950. It's glitched. What'd you get? And we would round that to 8.11 feet. Right of A. Right? right? And then R would be equal to 950 pounds. Down. Where do I got you stumped, Devin?
3,200 plus 3,600 plus 300.
No, why are you
What's
adding the
900?
300? The 300 is not a moment. 300 is a force. This moment is 300 times 3, that's 900. This moment is 450 times 8, that's 360. 200 times 16, that's 3,200. These are your moments. These are your forces. Yeah. You're glitching.
There we go.
Controller glitch. Yeah. I have to say, I think it's pretty funny when, I don't know, follow this Instagram thing that's like an NBA thing. Now and then basketball players just like lose their mind because they play so many games in a year. They're like glitch on the court. They just stand there and watch. It's pretty funny. Really good players do it. All right, let's do the next one. Unless there's questions on this thing. My red pin's dying. Good, we're good with that? All right, that's vertical. We're gonna do another one here in a little bit that has an angled force on it, which is complicated. All right, this one was your first distribution. What was our strategy with distributions? Yeah. Get rid of them is our strategy. Get them off there. So how do we get them off there? We calculate the area of the distribution. So if your distribution looks like a parabolic curve, some evil engineer gave you this distribution, right? You have to calculate the area of the parabolic curve. Hopefully it's a second degree parabola. That's pretty common. Third degree, less common. Fourth degree, less common. But wind creates this, like if you take this and put it vertical, this is what wind does to it. Creates these kind of loads. So you don't have to know calculus to do this. Those equations for area of these shapes are in the cover of the book. Look them up. Also, it's going to give you the geometric center, like where that is. Look it up. So if you get a weird curve, look it up. All right, don't break out your fancy calculus equation. Don't have to. If your distribution is complicated, like this maybe, make this load curve, but maybe a pile of gravel or something. It's approximating, right? So if you get a complicated load curve, you can break it into geometric shapes and do them separately. We're going to break this one into two shapes, two rectangles, right? So you could break this into a rectangle and two triangles and just concentrate those. 1, 2, 3 concentrations, get rid of the distribution. So you'll be able to see that in the recording, but that's all right. You'll flash back to the memory, I'm sure. All right. So we're going to calculate the area. When they give you this, they're giving you the height of their rectangle. So when I draw it, I like to kind of just remember, hey, if they're giving me 2 kips per foot, they're giving me the height. If they give you 2 kips per foot here, and then a 0.5 kip per foot here, they're giving you the height of these things, okay? The length will be given in the distance of the beam or whatever you're working on. All right, so what's the area of this one? 14 times, yeah, 2 kips per foot. So if I write it out, it's 14 feet times 2 kips per foot. And what happens to the feet? Boom, and we're left with kips, right? 28 kips. Where's it go? Geometric center of the shape. Geometric center of the shape. So this triangle's right here, this rectangle's in the middle, this triangle is here. For this rectangle, it's in the middle. Rectangles are the easiest. And it turns it into a force, 28 kips. Now that distribution is gone. Okay. How big is this distribution? 10 feet times 1 kip is 10 kips. And where do we put it? Straight through the center. So this is 5 feet over. This one is 7 plus 10 is all the way over would be 17 feet. If I'm collecting them again at A. Am I? Yeah. It didn't say you could do it at B. There is no B. Right, but it didn't say where you collect it. So we could collect it at a different spot, but I'll just keep going at point A. Now the distributions are gone. And we just have two forces, a nice parallel system, right? So we have to collect everything at A. What are the vectors that are going to go at A? Yep, there's two of them, 10K and 28K. So that's the translational effect of our beam. And then we have to bring the moments over, right? What's the moment for the 10K? 50 feet.
Where is it?
Oh, it is, you're right. 50 foot kips. It's weird. Big kip feet. And then what about the 28? 28 times 17. Or 7/6. Kip feet. Good, everyone kind of get what we're doing? Moving everything to one spot, collecting everything. If these vectors are in line, you just add them up. If we had an X component here, we would add up all the X's, we would add up all the Y's, right? That would give us the two components of the resultant. We could get the result from those. We'll do one of those next. But this one, you're just gonna add them up. So R equals what? Yeah. 38 kips. It's a force. It's a vector. It's the translational force, the down effect. And then what's my moment summation? Sum the moments equals 526 kip feet rotating this way. Good morning. He's like, don't talk to me. I'm late. I'm talking to you all in one. Now here's my new beam. Here's my point A. I know because of this effect that this resultant is moving out onto the beam to the right, because this is the moment I have to create. So force out here is going to create that kind of rotation. So I know R is out here somewhere. I know R is 38 kips. I just need this distance. So same way as above, we divide the moment by the force and we get the perpendicular distance. So 526, 13.84 feet. Is that right? When we place it out here, we don't put a moment in here because that moment's over here at A, right? Placing it out there represents the moment, so. 38 kips, 13.84 feet right of A. That's on the beam, yeah? because the beam's 24. You can get the resultant off the beam. That does happen, so don't freak out if that happens to you. Remember, the resultant is the effect. It's what the beam's feeling. It's not really an active force on the beam because these are the active forces up here, right? They're the actual real forces. This is the collection of the effects. And the effects can be off the beam. Telephone pole resultants are often above the pole, out there in space somewhere. So that's not uncommon. Yeah,
The purpose of doing a calculation like this leads into like strength of material.
that's
right?
exactly right. Because now I would go, oh, I got 38,000 pounds right here. So what's that gonna do to this beam if it's supported here and here? It's called deflection, right? And it's actually, let's see, 13, what's halfway? Halfway is 12. So it's a little past halfway, the resultant is, right? So here's the center line of the beam at 12 feet, and we're at 13.8, correct? So we're a little asymmetrically loaded, right? Not symmetrically loaded, but a little bit off. The deflection point shifts over a little bit right here. So if I'm gonna calculate maximum deflection, I know where it's gonna happen. It's at 13.8 feet. That's important. I gotta know where that is, so I can build my deflection equations, right? Where's the maximum bending stress occur? Do you think? At the resultant, like where it's feeling it, like it's here. Maximum bending stress is right there, at that spot. Looking at this, I don't know where it is. I kind of have a feel for what the beam's doing. It's doing this. But I need more than that in strength of materials. I need to know where it is, where this resultant's happening. So my primary design tool is bending stress. We bend stuff, right? We don't want to bend it anywhere near its limit. So we have to calculate bending stress. So we have to know where maximum bending stress occurs. That's why we're doing this. Good question. I was tempted to do a whole problem today to try and raise the energy level, but we're doing okay, I think. Bring coffee, that might help. All right, good. Questions? Comments, concerns? Political statements, anything? No? I appreciate that. All right, turn them in. I don't listen to the news this time of year, I just turn it off. I don't. I had such a peaceful 50-minute drive with the radio off. I turned this one in. 58 degrees when I walked out of my house today. I was like, what is happening?
It's nice.
It's crazy.
Yeah.
Was it cold back east?
At night, a little bit, no?
Yeah, yeah. You can turn in anything until next week. You're a special.
Well,
I'm still trying to get caught up.
I did most of them.
Okay.
I think there was one or
I
two
saw
that I didn't do.
And I graded them.
Did I turn them in? Or did I turn them in?
Hey, should they?
No, because I just got into
Oh, okay.
status.
Somebody else did.
Yesterday I got into status.
Oh, that's
so I have
right.
the thing on
That's what I
now.
was gonna say.
Right,
Yeah.
I'm missing like one or two, but I'm doing a little
It's
move right
fine.
now and I'm not
Yeah. it's
sure where the ones that I did are. I'm gonna get those in.
Put it in one pile, yeah. I'll separate them, because y'all are so good at labeling over the signs.
Speed of labor. This one.
Put it in that same pile.
Same part.
Yeah, hopefully you have it labeled like,
Oh, yeah.
yeah, so I'll be able to go.
Also, good question, about this assignment. It's unfinished at home. Can I just turn it in? Submit?
Until next week.
Okay, just
I'm
physically.
taking late stuff, yeah.
Okay.
Yep.
Yeah, because I forgot about the 8 and 11:30, the first assignment.
So in the future, like next week, if it happens, you need to send me an email right away and say, hey, I forgot, or I had to work, or whatever
Yeah,
you want to say.
fair enough.
But if I don't get any communication,
It's gone.
I'm cutting it off.
That's
I
fine.
have 7 classes. I can't
That
start
is,
collecting late stuff anymore.
that's totally fine.
So we're 4th week, right? Everyone's
Yeah.
dialed in to what's happening. All right, perfect. Perfect. Do you need a break? Let's be honest here. Do you need a break?
I'm all right.
All right,
Is the lab for orientation due at the end of today? Because I'm waiting on my partner to finish his.
it's really hard with 7 classes, so I have to process like what
It's a
question,
lab right
what
after
class,
ping pong.
G101,
Ping pong.
ping pong lab, end of day.
Midnight.
Waiting.
11:59, you can submit that thing. I hope the whole system works for you. Yeah, end of day. Cool. That was a question about another class, just in case you're confused. All right. Let's do one. Let's do a vertical one. Might as well have some fun here. And let's do telephone pole. We should do it all the way out too, just for fun. I will not taper my telephone pole. Just for you guys, but I want to taper it because they're all tapered, right? I am gonna bury it in concrete though. And how tall do you think they are? Wow, that's an unusual number, I gotta say. Most people would say 50, 100. I like the 45 feet. I have no idea how tall they are. But I'm guessing they're a solid 45. So then we're gonna put some loads on top. So we're gonna say we have 300 pounds here. And we have 280 pounds here. That's like kazoo height times 3, I think. Bless you, times 3. And then we're gonna put this one on. 100 pounds. And an angle of 7 degrees. Okay, I'll let you capture that. 45 feet tall. We will say that they all kind of come together up here at a single point. We'll just use the center line of the pole. We should put one more on. Don't you think?
Yeah, why not?
Sure. We'll put it down here. Some kind of a guy thing, guy wire, which goes all the way down to here, right? But I'm just gonna put it on like this, and it's gonna be 200 pounds. And we'll make it, that look like 50 degrees maybe? There we go. So some kind of support wire partially down, anchoring this thing on. And I just made up all these loads, right? Who knows? Who knows what we got? So the problem, the full problem, like if we were gonna do an analysis, so this is, if you're given everything, this is, everyone know what kind of trees we have in this area? We have cedars, that's true. Do you think we'd build our telephone poles or power poles out of cedar? They'd last long, but they're not as strong. Doug fir. Douglas fir telephone pole. So if we were doing strength of materials, we'd need to know what that thing is, right? And then we're gonna encase it in concrete down here, whole bunch of concrete. So this is fixed. It's like locked in, right? So statics needs to tell strength of materials what the resultant is and where it acts. So that's our job. Where do you want to collect the forces at? We can do it at A, we can do it at B, or we could do it at C.
See,
How come?
it just, you only have to move one.
Yeah, you got a big group of them up there at C. It's a great idea. If you choose A, how many forces do you have to move? 4. If you choose B, how many do you have to move? 3. If you choose C, how many you gotta move? 1. Okay? So when it becomes your choice, move them to wherever the forces are, if there's a big collection, right? So moving them to C, we're just gonna move the 200. The way to move the 200 is to find the components of the 200 and move the components. Okay, so we have Fy of the 200 and we have Fx of the 200. So if you have forces at an angle, find the components, move the components. A lot easier. All right, so I'll use this little triangle down here because I have the 50 degrees in here. And I'll find X and Y components. Since that's part of your, potentially part of your quiz on Friday. You do it, I'll do it, we'll all do it individually, and then we'll compare our notes on finding these components. Everybody got it? 200 pounds, 50 degrees. Can I blank it out? I'm gonna take that as yes. Sad my red pin's done. Did I get them right? 128 down. 153 left. Okay, good. Now we gotta move them up there. So when we move them up, we literally just move them up. So the Y is gonna come up to here. And it's gonna be 128.557.5, and the X is here. 153.2088 pounds. Right, so we move them up and then we have to bring their moments with them. Right? Moments, force times distance. So here's the X. Here's its line of action. Here's the perpendicular distance. So we need to know where this spot is. I didn't tell you, but we got to know it. So we just need to make that up. I'm going to put it at 20 feet. From here to here, so that means up here it's what, 25 feet? We would need that information, where that vector is. So what's the moment of the X about point C? Because that's where we're collecting things, is at point C. It's gonna be 153 times 25. Don't round it, use the whole number. I get 3830.2222. Yeah, what's the rotation? Careful. This rotating about C is like this, negative. And its value is 3830. 222 foot pounds, right? That's the moment. That's the moment with the X force. You're ruining my question. What's the moment for the Y force? Look at the line of action of the Y force. Does it go straight through C?
So it doesn't have a.
It doesn't have a distance, so it's force times 0, which is 0. There is no moment. The Y force, it just gets transferred up there, but it creates no moment about point C. So we only have one moment, 3830 up here, right? Now everything is at point C. We can collect it all. So the way to do that, I'm going to redraw point C right here. C. And we need to collect all of the X forces and all of the Y forces. That's the way to do it when you have forces at an angle. So we have one force at an angle. The rest of these are just X and Y's, right? So,
Fine, 280 and one. Make force, or is that too?
oh, absolutely. 300, the 280, the 153, they're all in the X. We can just combine those.
You have a minus the 300, it's going the opposite way, so add the 280 plus 1.
So the 300 is positive,
Right.
280 is negative, the 153 is negative. So yes, we have to keep their signs absolutely correct. But wait, there's another X force. Because when we collect all the X's, we want all of them. What is it? Yeah, the X component of 100. We need to know what that is. So the notation typically looks like this. Some forces in the X, adding all the forces in the X, right? Minus 153.2088 minus 280 plus 300. I'm just working my way across the top. And now I need the X component of the 100. That would be what? Cosine 7 degrees times 100. Sometimes you'll see it written like that, where they just put the equation in. Because that is equal to the X component of the 100. All right. You could calculate, you could come up here and calculate it somewhere and just put the number in also, that'd be fine. 99.2546, right? You could do that. So this then is gonna be equal to the X component of the resultant. So I write it R sub X. And add them up. I get a minus 33.9542. pounds. Means it's going that way. Anybody else get that number? Yeah. And we do it with the Y.
So,
Yeah.
even if we have like the Y values go, the one Y value from the 200 pounds. Since that's going straight through C, why wouldn't the 300 and the 280 and the 153, because they are going straight through C as well?
Create moment. They didn't. We didn't do any moments for those. We only did one moment and that was for that component right there, right? But you're right, the rest of these, we didn't have to do moments because they're all going right through C. That's why this spot is so delightful. If you did down here, you would have had to do 1, 2, 3, 4 moments. Yeah. You're gonna get the same answer if you don't make a mistake. You're just gonna work a hell of a lot harder.
Is that ever up to us? Like, it seems like which one you pick would be dictated by like.
No, it's up to you. Yeah, if you're asked to do an analysis of system, they're not gonna,
They're not gonna specifically say we need a
No.
moment about A.
no. They just need to know where the resultant is. Right? Where you collect everything, if there's no mistakes made, we'll give you the same resultant at any point that you collect. There's just easier spots and harder spots.
So does that mean that the results in C is the same as the results in today?
The magnitude would be the same, exactly.
Oh.
Yep. Cause you're, all these vectors, you just moved them up here, right? So if you moved them to A, all of them would look exactly the same at A. The moments would be different. But the vectors would be exactly the same.
And then not gonna be a time where they need a moment at a specific point, like they.
Oh, no, we definitely need moments at specific points at times.
Okay. So
So
there could
that's
be a-
different than resultants.
Right,
Moments are what we put into the Benny stress equation. So we absolutely want to know moments at different spots. Really, we just want to know where the maximum moment is, but sometimes we do intermediate spots.
it's weird having things.
Yeah, reversing this back. All right, what'd you get for Y?
You just have like the one, two.
128.5575. Oh, right, that one. Sorry, I'm maximizing my little projector thing here. This might help a little. There we go. Right, that was this one. That was the Y component of this thing that we moved up. 128.5575 is in the Y. And then the Y component of the 100, right? Which is gonna be what? Sine 7 degrees times 100?
And it's negative is down.
12 point.
Yep. Force, the sign of the forces is whether they point up or down, or right or left. Yep, so we have two negatives. The negative 128 from the support wire. That was this creature. And then the down force of the 100. That becomes our Y. Is it 140? 140.744446. And it points down. Correct? So this is what we have going on at C. A little x and a big Y, R Y, R X. And a moment of 3830.222 foot-pounds. It's up at C, point C. Agreed? Good telephone pole design. Why do I say that? It's a good design.
Most of the force is going straight.
Most of the force is coming straight down into that concrete. The only force that's trying to bend the pole over is what? Is the X component. That's the only one trying to bend it over, and that's only 33 pounds. It is carrying quite a moment because it's so far away from the concrete. So 33 pounds at 45 feet, that's a bunch of lever arms, right? All right, so what would, like, if the question was, what's R? What is R? Yes, that agreed there, right? X squared plus Y squared, blah, 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 square root. No, because they're just gonna square out anyway. So you don't have to. What do you get? 144. 0.78 pounds. And they would typically want to know the angle. So maybe the angle to vertical, since this is a vertical problem. That would be good information to know right here. We still have to move this resultant out onto the pole. Because it's carrying a moment up there. So that means the resultant is not at C, but it's somewhere else. Whenever we have this carried moment, that means R is not here, it's down on the pole somewhere. All right, so that angle would be what? Inverse tangent X over Y. So I take the X, the 33, divided by the Y, 140.74446, divide inverse tangent, 13.56 degrees. So if I want this angle, and I use tangent, that's opposite over adjacent. So it's X over Y. So I took this and divided by this and took the inverse tangent. It's that trig function magic. You can break it out at a party and amaze people with it.
They'll probably figure out.
Unless they're another engineering student, and then they'll be like, oh man, that's so damn cool. Let's do this.
I don't think engineering students are gonna be doing parties.
Evan.
Look at us.
So much to learn. Inside of you are crazy party people. All right, let's do the final step. Like, where is it on the pole? So I'm gonna draw the pole again. Maybe I can keep most of this if I draw it off to the side. We'll see. Here's my pole. 45 feet. Encased in concrete. And up here, I know I have my R. I'm just gonna kind of highlight it in because it's not really there. But it's this, the 144 at my 13 degrees, right? And it has a moment up here at 3830. So here's the deal. This is the interesting part. Your Rx and Ry are here. And we're gonna take this thing and we're gonna move the resultant down here to where it really is. Right? And we're gonna let the moment move it for us, just like we did before. We're gonna take the moment and divide by a force. Right? The force you want to divide by is the force that's creating moment. It's X. Y is traveling right down to where we're going to put it and goes right through where we're going to place it. The Y force creates no moment. It's all just straight down force. The X force creates all the moment. So we're going to use our X and our moment. We're going to take our moment divided by Rx to get our perpendicular distance. And that'll be a distance down the pole, perpendicular to X. So all the moment of a telephone pole is carried by the X components of whatever's going on. So I take the moment 3830.222 and divide by the X component of 33.9545. What do you get? 112.8 feet. Yeah, that's crazy. So where is it? It's like in the ground somewhere. It's where this resultant is. It's way down, like way down here. So that's just telephone pole stuff. It's weird. We actually don't use that for analysis. What we would use is this. Rx is creating a moment about right here, trying to tip this thing over, right? This is what's going on. A big rotation down there. So we would calculate the moment here of Rx, and that would give me my moment down here, and that would be the largest bending stress on a telephone pole. And I would see if that piece of wood could hold it. So this is a little bit of a unique problem, a pole, but that Rx is critical. And Ry is critical too, because this concrete and soil can only hold so much. If we load it too much, it's gonna just squish into the ground. So Y is important too, especially with our soil pressures here. So this has to push up equal to Y coming down. And if it can do it, it's a good pole design. If it's too big and this soil pressure of 1500 PSF, if it can't hold it, then it's going to sink it into the ground. We should have made the concrete bigger, which would have given us bigger footprint and more soil pressure, right? If we just stick the pole in dirt and don't put any concrete around it, then you got an area about this big that's got to carry the load. And with only 1500 soil pressure, it's gonna just punch it. Pretty soon your power lines are hanging on the ground, and that's not good. Your pole's in the ground. Good? All right. That is angular ones. I think you have one to do. It's 42. You have two problems, but only one of them has an angled force, and it's back to horizontal. It's this thing.
And with the quiz, are we gonna have
I don't know. See how mean I get on the quiz. I haven't made it yet. But I have two problems. One will be super easy. So don't forget your units. Don't forget all the information. That's what takes these little points away that are just annoying. You get the right answer, but you don't put a unit on. Or you get the right answer and you have it out to 50,000 places of decimal points, right? Round it to 2 places, put a unit on, make sure you get your directions right. The number is only part of the answer, right? Might have everything. So you have one problem, super easy. I don't know. It might be like find the components of a force kind of thing. And then you'll have another problem that'll be a resultant. Probably not an angled force, Gina. That would be kind of mean since we've only done one of those. Probably a parallel system. Cool. Sound good? Everyone knows I'm out of here now and I'm not holding ET116. So if you're in ET116, no class, advanced AutoCAD. Okay, we're done. Good job. See you Friday.
My box.